RiTri05 deals with Pythagorean triplets. We know now that a right triangle with three sides creates a relationship such that if I take the smallest side, smallest leg, and I square it, and I add to that the square of another leg, that it will give me the square of the hypotenuse. 9 plus 16 is 25. It will always, always, always work for any right triangle. Now, usually when you practice with these problems, you use 3, 4, 5 a lot. It starts to build this pattern in your mind that maybe it's sequential numbers that make right triangles. And so it might be natural to, for instance, say, well, let's try some other sequential numbers like 4, 5, 6. However, when we try 4, 5, 6, we put a question mark there because we don't know if it's equal. 16 plus 25 is 36. 41 is not equal to 36. So in fact, it's not the case that any three consecutive numbers will make a right triangle. Turns out, oftentimes, the missing leg, for instance, let's say that I know that 4 and 5 are these sides, I'm looking for the third. 16 plus 25 equals x squared, 41 equals x squared, x is equal to the square root of 41. There is a right triangle with these two legs as 4 and 5. However, the hypotenuse is not a whole number. It's not a nice, easy, solid number without any decimals. In fact, this number comes out to be an irrational number with no termination to it. So it's special. It's important when we find groups of numbers that fit together to form triangle sides of a right triangle, and they're whole numbers. That's called a Pythagorean triplet. So one of them that we've used a lot is 3, 4, 5. Another one that we find is pretty familiar begins when I have a hypotenuse of 13 and a long side of 12 and an unknown short side. So x squared plus 12 squared is equal to 13 squared. X squared plus 144 is equal to 169. X squared equals 25. X is equal to 5. So another Pythagorean triplet that works really well for us is 5, 12, 13. Now, there are lots of Pythagorean triplets out there. However, what makes them useful for us is not just that our simplification process is easy, however, that we should be able to recognize them and quickly identify them. In fact, I do have several friends who are in the trades of construction, and when they want to produce a right angle, they want to construct something with a right angle, what they often do is construct a triangle that is 3, 4, 5, knowing that by that fact it makes it a right angle. In fact, we'll be getting into RiTri06 that deals more with that in a moment. What I want to point out, though, is that if you're given, for instance, 6, 8, and an unknown side here, you could go through the Pythagorean theorem to solve that. However, you might also notice that this is 3 times 2. This is 4 times 2. Well, if 3, 4, 5 works, then any dilation of that triangle is also going to be a right triangle because it's going to be a similar triangle. So here's a dilation with a scale factor of 2. 3 times 2, 4 times 2. This side must be 5 times 2, or 10. In other words, other common triplets include dilations of these original ones, like n equals 2 here. What if we chose n equals 3? We could do that. Could we choose n equals 10? Sure, we could do that. In fact, we could choose any combination of values whereby they're in the ratio of 3n, 4n, 5n, and of course n is a whole number. Same is true over here for the 5, 12, 13s. We could double it. We could do it times 3. We could do it times 10. We could do anything that is a dilation of the 5, 12, 13 triangle. And again, there are other versions of this. 7, 24, 25 works. Boy, there's a lot of them out there. However, if you're ever looking for a Pythagorean triplet, you can also use Plato's formula. Now, Plato's formula didn't identify a way to come up with all of these, but it did tell you a way where you could come up with a set of Pythagorean triplets if you wanted to. Choosing a single value n. Someone give me a value n. 3. Okay, thank you. So I'm going to have three sides. One of them is going to be 2n, which in this case would be 6. One of them is going to be n squared minus 1, which in this case would be 8. And one of them is going to be n squared plus 1, which in this case would be 10. Well, notice that this is one we've already identified. However, when I choose a number like n equals 5, I'm going to get 2 times n equals 10. N squared minus 1 is equal to 24. N squared plus 1 is equal to 26. That's over on this side. So it's not all just these triangles. But the formula says if I have three sides, they are 2n, n squared minus 1, and n squared plus 1. You could derive that if you wish. That is RiTri05, Pythagorean triplets. You should be able to identify them and use them to make your job easier in finding missing sides.